first and foremost, thank you so much for taking out the time to stop by. I really appreciate that.
Sure, happy to do it.
For the viewers who may not recognize you, could you let them know what your name is and definitely where you're from?
My name is Richard Milner, and I'm a professor of physics at MIT, Cambridge, Massachusetts.
Okay. Now, can I ask you, when did you develop this passion for physics?
So I grew up in Ireland, a little city in the south called Cork, and I guess in high school I had a physics teacher, and there was a local library that I used to go read books, and I guess, I don't know, I got interested in physics. So then I went to the local university in Cork and got my undergraduate degree in experimental physics. And I guess I really liked the subject. So I wanted to go further, which I really couldn't do in Ireland at that time. That was about 1978. So I did a master's in theoretical physics and general relativity in Ireland under somebody who had done a PhD in Princeton on that subject. And then I applied for graduate school in 1979, and I got admitted to Caltech. And that was a dream. I wanted to travel. I'd never been on an airplane, so I flew from Heathrow to Los Angeles, and then spent the years 79 to 88 at Caltech, first as a graduate student and then as kind of a postdoctoral researcher, and then moved to MIT on the faculty in 1988, and I'm still here. So,
wow, that's amazing. Now I have to ask you this because time when you go to different countries, you experience like a culture shock. Going from Ireland to California, what was that like? Was that an easy transition for you?
It was culturally, but let me tell you a story. So I was there a few nights in the dorm, and I had jet lag. So I would hear rain at night, and then I would get up in the morning, and this was August 79. It was beautiful. That went on for a few nights, and I said, this is an amazing country, where it rains at night and is beautiful by day, because in Ireland, it kind of rains most of the time. So like on the third or fourth night, I got up to see the rain. It was a sprinkler system. I had never heard of a sprinkler system in my life growing up in Ireland. So that's kind of that gives you an inkling.
Oh, wow. I appreciate you sharing that. Now I have to ask you this, like a lot of times when people hear physics, they think
Yeah.
of something that's hard or difficult or challenging. What exactly is physics?
To me, physics is one of the most powerful ways of trying to understand objective reality. Of course, it does it in a very, mathematical, objective way. But I just always was impressed how deep it was and how you could try to understand things from very basic principles. And that's what physics is. And physics is always hard. That's what I tell people. Like, you have to kind of accept that to be a physicist, that it's always hard. It's always difficult. I mean, even when I teach freshman physics, you can't assume that it's trivial. And that's why I like it, because it's always challenging, but it's always interesting. And it has this unique perspective on reality that I like.
Okay. I appreciate you breaking that down. Now I guess I could ask you this. What courses do you teach?
I just finished the graduate nuclear physics course at MIT, but I often teach undergraduate freshmen in mechanics, Newtonian mechanics. So there would be the two principal kinds of courses that I would teach at MIT.
Okay. Now I can ask you this, since you've been doing this for quite a while now. What are your thoughts on the effect of technology and animation and AI and how it relates to, the work that you do?
Yeah, well, to me, all these are tools. I particularly got interested in the animation and trying to do outreach to colleagues or young people who, don't have a graduate degree in physics, but you want to convey the essence of that. And AI is something physicists have been doing pretty much forever. Some form machine learning, but I think it's now become very ubiquitous in terms of like society, and it's like everything else. It can be used for ill or it can be used for good. So one has to be aware of that, I think.
Definitely, definitely. Because regardless of who I interview, whether it's music, whether it's film, whether it's, any type of field, they have their perspective on AI. And some people, it's been a struggle, because things are changing. It seems like so fast.
Yep. Yeah. Yeah. It's kind of the next big change of our time and how we adapt to it. And, we'll see. It's, I think, again, it's a tool, and people have to each individual person has to exert good judgment about things. If you just kind of don't think for yourself, that's dangerous. And I think that's one of the things with modern technology and social media, is that the ability to think independently is a little bit harder.
Yeah, I definitely agree. Okay, now I wanted to ask you about the visualizing the proton project, if you could speak on
Sure.
what that is.
Yeah, so this is work done with a colleague, Rolf Ent, a fellow physicist at a laboratory in Newport News, Virginia, called Jefferson Lab. And he and I have worked together over about 2 decades, and we had this idea to animate. And so the idea is the following: that the quantum world, once you get into the atom and the nucleus and the subnucleus, it's a quantum world. And in the quantum world, everything is always moving. There's nothing static. And that comes from a very fundamental aspect of quantum mechanics. So, when you try to picture the hydrogen atom, it's typically the proton is this ball in the center and the electron is this dot, kind of orbiting it. And we felt, particularly for the structure of the proton and nuclei, that we could convey a lot of the understanding of how nuclei and protons are built and how they behave, if we could animate it. So, long story short, in 2018, we finally, great credit to a center at MIT, the Center for Art, Science, and Technology, gave us some money. And what that then forced us to do is, well, we've got to find an animator. We're physicists, Ralph and I, so we couldn't animate. So we searched for over a year with great help from colleagues, Chris Bobel and Joe McMaster at MIT, highly experienced in video production. And we found a fantastic animator, James LaPlante, who's got a company, Sputnik Animation, in Portland, Maine. And that was the final piece. And then we did the proton, visualizing the proton. So we had to take what's known about the structure of the proton from various experiments and then build this kind of animation model. And we did that. I think it was released in 2020, and it was very, very well received. And so we've continued. We're still working together. We actually just met earlier this afternoon on Zoom, but we most recently have visualization of the nucleus, where we show the protons and neutrons. And now we're looking at specific aspects of nuclear physics, particle physics. And we're going to have a succession of these short videos. So then we did the animation, and we had to tell the story. You can't just show somebody an animation. You've got to explain it. And so we built these, I think we started with like 8-minute videos. And now we're down more like around 5 or 6 minutes typically. And we put these on YouTube and just make them available. And they've really been, I think the one on the nucleus has over 500,000 hits, so we're happy.
Wow. Okay. Okay. Now I can ask you about this. You said it took you a year to find the animator. So how much time have you spent on this in totality?
Well, it's a. I'll be blunt. It's a hobby. You know, I teach. Ralph and I are professional physicists. We teach. We do research experiments. We travel. So you know, nobody. We get no personal compensation or take any or seek any for this work. This is kind of a service work that we do. Of course, James is he's an animator. He needs compensation for his work and for his infrastructure, his computers, and all that. And so, we try to do it as cheaply as we can. And so, it's a part time, very much a part time effort, but one we really love. We really like doing it, and as long as people react positively, we'll keep doing it. And we seem to be getting. It's easier to get little bits of money. These things take, $25,000, $30,000 each to kind of make, so, it's a significant amount of money, but it's not unobtainable. If you go to the right sources, we've been able to get some money. So.
Wow. Okay. Okay. Now I can ask you. You have a book, the Hermes Experience, the
Mhm.
personal story. If you could speak about that a little bit.
Sure. Yeah. So when I was at Caltech in the late 80s, there was a very puzzling result that came out of CERN that somehow the spin of the proton, we know the spin is a half, but where does that come from? And it should be built from the constituent particles, which are the quarks and the gluons. And they found very, very small contribution from the quarks to the spin of the proton. So Hermes was a really innovative experiment, a new type of experiment that was built in Hamburg at an accelerator in Germany. It was kind of a transatlantic collaboration. There was a whole European component, and then there was a North American, US, Canada. And together we built this novel experiment to search for, to study the spin structure. And one of the exciting things we did is we came up, and other experiments and theorists, we didn't do it alone, but the Hermes experiment was certainly on the vanguard of a whole new perspective on the structure of the proton. See, the original experiments that were done at SLAC got the Nobel Prize for Friedman, Kendall, and Taylor. You smashed the proton. You basically hit the proton with an electron. You smashed it into pieces, and from that you could deduce that there were quarks and what their momentum was. But nowadays, there's a new class of measurement called deeply virtual exclusive process, where you don't smash the proton, you leave the proton intact, and you make another particle. It could be a photon, it could be a meson. And Hermes helped pioneer that, and that is now kind of the future 21st century physics. And we are very excited about the possibility of a new accelerator on Long Island called the Electron Ion Collider, which basically will pursue this study and these set of measurements to much larger kinematics, so that we can study the proton and the nucleus in the round, basically, and not only in the longitudinal direction, but also in the transverse direction. And so Hermes was really a great experiment, ran from 1995 till 2007. And somebody thought it would be a good idea to write a book on it. It wasn't my idea, but they approached me. I helped initiate the experiment. I was one of the initiators. And so World Scientific approached me, and the first thing I realized is that I needed a colleague because, as I said at the beginning, there were two aspects. There was the North American, which I was part of, but there was also the European, and I needed a colleague from the European side, and that turned out to be Erhard Steffens, who was the co-author, and that worked out really well. So we could write, the origins of the experiment from the two different perspectives, and Yeah, it was a lot of fun. It was a lot of work, but actually a lot of it got written over COVID. So COVID was a good time to be hunkered down writing a book. So, and of course we did it over Skype, I think mainly, and Zoom, but yeah.
Okay. Now, okay, ask you now, how long did it take to write that project?
I'm going to say about 3 years, you know, about 3 years. Yeah. Yeah.
Okay. Now, do you have any other upcoming books or documentaries in the works?
I don't right now. I mean, what we're focused on are these short animations. We have a whole series. We have one. We hope it'll be final in a month or so, and then we have two or three more on the drawing boards that we want, and funding to do them, I should say, that are coming up later in the year. The other thing that Rolf and I have done, and was motivated by the animations, is we have developed a set of posters that describe the history of the structure of matter from the earliest times to the present. And we're just finishing those, and we'll be releasing them. There'll be a video, a YouTube video associated with that. It's coming from Jefferson Lab, so you might want to keep an eye out for that. But we basically, one of the major targets there is high schools. We'd like to get some of these poster series in the high school, so young people could learn about, how humanity kind of developed the present understanding of the structure of matter, which is the basis of our modern civilization, that we have. And so to understand that is important, I think. And it's inspiring, actually, to see.
Okay. Now, for the viewers, if they want to keep up with the series, what's the best way for them to do that? Is it YouTube, or is it a website, or?
We have a website at Jefferson Lab that I can certainly make available. Yeah, YouTube. They'll definitely be on YouTube. But there is we've just put together a central website where we collect all of these, and it's at Jefferson Lab. So that's, I think, the best way to keep track of it.
Okay. Yeah, I'm sure they'll definitely tune in. It sounds exciting. I had wanted to ask you about a few terms. You had kind of touched on a few of them, but if you could speak. Okay, now, what are structures of matter?
Okay, so basically understanding what matter is made of. So it started in the time of the Greeks, in the ancient times. So the Greeks had different ideas about what matter was made of. I mean, you had a guy like Aristotle who thought about earth, fire, water, things like that. And then you had others, I think Democritus was one of them, who said, well, there's something indivisible at the bottom. That's what the word atomos in Greek means, indivisible. So that there's a basic unit of, and to be truthful, not much happened from the time of the Greeks till, about the 1400s, 1500s, when we had then people like, Galileo, and of course, the big person is Isaac Newton, developed laws of motion. There was a real flowering in Islam in the 900s, about 10,000. And most of the Greek texts about science ended up being translated first into Arabic because they were interested. The Europeans, like they had the Dark Ages. The church basically believed Aristotle's viewpoint, and there was no discussion. And so there are people like in the Middle East who invented algebra, chemistry, distillation, all these important things. Coffee, they invented coffee brewing in there. And so then I think you started to have an understanding of optics, and you started to get like a microscope, maybe around 1600. And then they started discovering crystals, that, certain rocks or objects in the ground were crystalline. They had a certain shape. And then I think the whole concept of an atom, and it was the 1700s. You had gas laws developed. Um, you had the periodic table, mid to late 1800s, where, for example, Mendeleev in Russia tabulated all the chemical elements and showed that they were basically ordered in an ordering based on their properties. And then, you had Maxwell in England had developed the equations of electricity and magnetism. And then, the proton, the electron was only named in the late 1800s. And so the nucleus was discovered in 1911 by Ernest Rutherford. And then you had quantum mechanics, you had the Bohr atom, and that's the history, basically the history. So you had the basic concepts, 2,000 years ago, but really nothing happened till about 1600. And then now, we have global positioning systems on our phones that are based on 32 atomic clocks in orbit around the Earth. They use quantum mechanics that have relativistic corrections. So the laws of physics are kind of the basis for our modern human civilization, but unfortunately, most of our citizens they can't understand it. They know what it is roughly, but I think it's really important for us physicists to kind of make the effort to try and find ways to explain to people like how this is the way it is. So.
Yeah, definitely. I take my hat off to you. You're doing some very, very important work. I'm definitely appreciative of the work that you have done, and I definitely look forward to the work that you have coming in the future.
Good, very good. Yeah, no, it's any way I can spread the word, and particularly through your excellent podcasts, I'm very happy to use them.
Right. So we're about 22 minutes in, so I pretty much covered everything I wanted to cover. So, like I say again, I thank you for stopping by. It's definitely been an honor, and I'll definitely share the link so the viewers can check out, the videos that you have out and the ones that you'll have coming out.
It was a pleasure talking to you. Take care.
All right, take care. Bye.
Bye.